So we get to jump straight in. So last term, if you remember, we finished up talking about aromaticity. And we got a little bit into the reactivity of aromatic compounds, but we really stopped at reactions at the benzylic position, right? We didn't talk about reactivity off of aromatic molecules themselves. So let's take a look at some of the problems with this. And to do this, we're going to do a compare and contrast. Let's say I've got cyclohexene and elemental bromine. We know we can do addition reactions with this. And will the bromines be installed syn or anti? Anti, right? So you'll get one bromine facing the opposite direction of the other bromine, and you'll face or make a mixture of enantiomers, right? All right, if we think about doing this with benzene, we get no reaction. Why? So stabilization due to aromaticity, right? So what John was saying is basically this molecule is so much more stable that the activation energy is too high for us to overcome. Does anybody else have another explanation? Let's think about the theoretical product for this. All right, if we think about the theoretical product for this reaction, this is not observed, so let's be clear about that. What do you notice about the product for this reaction? Is it aromatic? No, so we've broken aromaticity. So not only do we have a really high potential activation energy, we've broken aromaticity, we're making a really unstable product. That means that this reaction is just simply not going to be spontaneous. Does anybody have another reason? So in particular, why is this a decent nucleophile, and why is this double bond not a very good nucleophile? It's not a true double bond, right? If we think about resonance, the double bond that I've highlighted in orange is really more like a bond and a half, right? So it is like a pi bond, but really it's kind of in between a pi bond and not a pi bond. It's kind of a bond order of 1.5. So that's the big difficulty with trying to get aromatic molecules to react. So let's make some notes. It would break aromaticity. It's a bad nucleophile because it's not a true double bond. And it would lead to a less stable product. I should kind of put in a little bit more detail on that first one. This essentially means that it has a super high activation energy. Yep.
So if you put a lot of heat or energy into it to make that reaction happen, would it just, as soon as that energy was no longer present, would it just reverse then?
Yeah, so the question is, if you applied enough heat, could you push this? Not really. The reaction overall is non-spontaneous. It just will not want to form that product at all. All right, but I'll show you a weird observation. Let me change colors here. All right, and this weird observation has to do with these exact same reagents. And what they found is if you take benzene and you take elemental bromine and you put in a little bit of iron, you can get this reaction to work, but it's not the product that you would expect. Instead, what you get is a bromine installed directly off the ring. Why do you think this is allowable without knowing the mechanism? Iron's doing some weird stuff. Well, what do you notice about the aromaticity? It's still aromatic, right? So this works because we're making a product that is still stabilized via aromaticity. Yep.
Does that have anything to do with the fact that iron's most part delocalized? Iron's electrons are delocalized themselves?
Kind of. So iron's doing something pretty peculiar here. So we'll get back to that, but let's think about what happened in this reaction. Is this an addition or a substitution reaction? Substitution, right? If we think about it, at one point we had a hydrogen coming off of this position. Now we're exchanging it for bromine. So this is called electrophilic aromatic substitution. And the big difference between this and what we were looking at above is we started out with an aromatic molecule and we end with an aromatic molecule. All right, so these mechanisms get kind of goofy, but one of the key features we're looking at here is instead of thinking about benzene acting as a really good nucleophile, instead what we're really focusing on is the strength of our electrophile, right? If we can't do much about the strength of our nucleophile, that's our only option, is to change the strength of our electrophile. So let's go ahead and dive into this mechanism and see if we can figure out what's going on. And we're going to start out with halogenation, so the example we just saw. So like I said, this will work with any aromatic molecule. It doesn't have to just be benzene. Benzene's just a classic example, so we're going to stick with that. And we're going to react this with Br2, and we're going to add in some iron. However, really when you throw in iron with bromine, you're going to make an iron-bromine complex called iron tribromide. And at the end of this reaction, we know we're going to substitute out one of the hydrogens for bromine. So let's make a note about this iron tribromide. And that is if you have 3 equivalents of elemental bromine and 2 equivalents of iron, and you react these together in solution, you'll make 2 equivalents of iron tribromide. So really that's what I'm talking about, is most of the time you'll see people indicate this with Fe. Really what you're working with though in solution is the iron tribromide. Does that make sense? So let's take a look at the mechanism. We know that the benzene itself isn't going to react with the bromine, right? We already ruled that out based on our discussions earlier, which means that the iron tribromide must be just doing something unusual. So let's start out with the iron tribromide. What's the geometry going to be for the iron tribromide so we can draw it out? It's going to be trigonal planar, right? So I'm going to kind of lay it on its side like this. And if it's trigonal planar, one important thing to note is that we've got this big p orbital kind of hanging up and down, right? So this iron atom in the center is sp2 hybridized. And over here, we've got a vacant p orbital. All right, so going way back to first term, do you think iron tribromide is going to be a good Lewis acid or a good Lewis base? It's going to be a great Lewis acid, right? Because it's got an empty orbital that wants electrons. All right, so if we've got this great Lewis acid around, it wants electrons. Really, the best source of electrons that are available would be one of these lone pairs coming off of elemental bromine. So one of these lone pairs off of elemental bromine can attack into one of these vacant p orbitals. Does it matter which side? No, not at all. So it can attack from the top or bottom, equal probability. Now we're going to make this funky looking complex. What do you notice about the hybridization of the iron now? It's sp3, right? So we've changed the hybridization. And if you remember way back to first term, we said that over here we've got our Lewis base. And we've got our Lewis acid. What do we call the product here? Does anybody remember? So it is a Zwitter ion. It has both positive and negative charge. But what do we call it when a Lewis base docks with a Lewis acid? It's an adduct. All right, so we've got this Lewis acid-based adduct where elemental bromines kind of docked with our super strong Lewis acid, that iron tribromide. And if we think about it, the bromine in particular right here just looks wrong, right? How many times have we had 2 bonds to a halogen before? I don't think we've ever seen that, right? So this is a really sad and unhappy element. Yeah, the whole thing really is unstable, but the bromine's the one that stands out the most. Iron can go through a variety of oxidation states. Yep.
Jeff, that iron, what kind of hybridization is the deal? Is it,
Oops, sorry, that should be sp3. I wrote sp2. Good catch. All right, so that bromine really isn't happy having that positive charge. It wants to alleviate that positive charge. So what's going to happen is we're going to have a super duper strong dipole where it's going to hog electron density away from the bromine coming off the edge right there. The weird thing with this is that means that this bromine over here is super duper electrophilic. I know I'm putting in a lot of words here. Does that make sense? So it's kind of this tug of war going on within our Lewis acid-base adduct. All right, so now we've got benzene kind of floating around. So that's actually going to be treated as our next reagent. And what benzene is going to do is it's going to act as our nucleophile, right? But it's a pretty weak nucleophile. All right, but it's still a nucleophile, right? It still has pi bond character. So it's going to go ahead and attack as a nucleophile that electrophilic bromine, right? That's the only electrophilic site we really have on this complex or adduct that we've made. All right, what do you think the next step is going to be? Are we going to have 2 halogens each with 2 bonds, or what do you think is more likely? It's going to kick off the electrons and give electrons to that super unstable bromine, right? That seems to make sense. Okay, so now we've got to kind of assess where we're at this point. We still have a hydrogen coming off of that carbon, but now we also have a bromine. And we must have a positive charge down here, right? In fact, let me go ahead and draw in the hydrogen over here as well, just so we can account for all of our important atoms. Does that make sense? So we formed this new cationic species. What's the problem with this cationic species? It's not aromatic anymore. Why is it not aromatic? So there's a few reasons, right? So if you remember going back to aromaticity, we said there were a handful of features that had to be satisfied in order for a molecule to be aromatic. One was we have to have a ring system. This is a ring. The next one was we had to have p orbitals in every atom along that ring system. What I'm seeing over here is we went to an sp3 hybridized carbon that has no p orbital, right? So immediately that means that this can't be aromatic and it can't be anti-aromatic either. This is really unstable. This has a special name because of it. This is called our sigma complex. However, some textbooks call this the rhenium ion. really what it is it's the intermediate where you've broken aromaticity from this nucleophilic attack, right? All right, so now let's think about the other thing that we should have floating around in solution, specifically that Lewis acid-base adduct we kind of kicked off as its own leaving group. So we can show that over here. The iron still has a negative charge. I'm not going to worry about dashes and wedges, but it's still sp3 hybridized, so it's tetrahedral. This is somewhat stable, somewhat unstable, but the weird thing that it can do is it can take these electrons from one of these bromines. Oop, sorry, that's a bad arrow. And it can reach over, grab this proton, clamp down, and restore aromaticity to the overall system. So if we think about this net reaction, what do you notice about the iron tribromide? It's catalytic, right? So we put iron tribromide in, we get iron tribromide out, so it's catalytic. All right, people tend to get confused in this last step. Oh, I also forgot one byproduct. What byproduct am I missing? Yeah, exactly. I'm missing HBr. There we go. And students will look at this and they'll say, I've never seen this sort of acid-base chemistry. Why do you think this acid-base chemistry is allowed? We're restoring aromaticity, and what do you notice about the iron? It's more stable, right? It's going from negative to neutral again. So this is actually allowed mainly because of that aromatic stabilization that's imparted to your final product. Do you have a question?
Did you want, in any case, a full sigma complex right now, where the positive charge is moving around the ring?
Yeah, that's a good point. So if we think about our sigma complex, it is stabilized through resonance. So you can go ahead and show the resonance structures for that if you want. In fact, I think in sapling, they might ask you to. However, as far as I'm concerned, unless I specifically say show all the resonance structures, you don't have to. Yeah. Yep, good question. All right. So chlorination can also work in this case. So let's take a look at the overall chlorination mechanism. So with aromatic chlorination, you're still going to start out with an aromatic molecule that has a hydrogen coming off. You're going to treat it with Cl2. However, instead of iron, the preferred transition metal that's commonly used is going to be aluminum trichloride. Don't ask me why. That's just what they show in the book. I think the iron one will also work. Really, you just need some sort of strong Lewis acid in order to facilitate that first step. And from this point, you can do electrophilic aromatic substitution and swap off that hydrogen with the chlorine. Really, the mechanism is really similar. Does anybody want to go through this mechanism again? No? All right. So we'll kind of leave it at that. This one's not as commonly done. Does anybody know why, logistically? Chlorine's a gas, bromine's a liquid. A lot easier to work with the liquid than a gas. So normally you see electrophilic aromatic substitution with bromines, not chlorines. However, if that's your goal, sometimes you're kind of stuck, right? So I'll show you some cool things you can do with this. So essentially, why does this matter? So let's think about it. Prior to today, if I gave you benzene as a starting material in a synthesis problem, you can do anything with it. If I gave you toluene, you could do something with it, but you couldn't do anything with benzene. Now we have the capability of treating this with elemental bromine and iron tribromide. To make this new molecule, what would this be called? Bromobenzene, that's good. Spring break didn't completely ruin you. All right, what can we do with this next? Can we do substitution? So let's think about it, right? If I have a nucleophile, can I do SN2 chemistry here? Yes or no? Can we do SN2 chemistry on sp2 hybridized carbons? No, we cannot. So this is a big no-no. We cannot do that. All right, if we can't do SN2, what's another option we could do? Okay, we could add elemental magnesium. If we add elemental magnesium, we can make a Grignard reagent where the magnesium inserts between the carbon and the bromine. And then what can we use Grignards for? We can use it for a lot of things, right? We can react this with an aldehyde. We can react this with a ketone. We can react this with an ester. What else? One more that we covered last term. So with an alkyne, it would really just rip the proton off of the alkyne and do acid-base chemistry, and we'd be done. Anything else? An epoxide. So really, we've opened up a new route through which we can do a lot of really interesting chemistry that we didn't have access to before. This is a really powerful tool, and I'll tell you point blank that reactions like this will be on your first exam. So this should be kind of a freebie point, right? Is if I give you benzene, what do you think your first step's likely going to be? Oh, we probably need to change the functional group to add something that we can maybe make into a Grignard reagent or something like that. So it's a really good first step that we have for a lot of these reactions. Does that make sense? All right, the big thing though, I see this every single year, is you cannot do SN2. However, I'm going to put an asterisk over here because as always with chemistry, there are weird exceptions. We'll cover those at the end of this chapter though. So for right now, don't think about SN2. Think about maybe turning this into a Grignard through which you can do other reactions with. All right, one last reaction for today. I think we should have time for this. Yeah. We'll do sulfonation. All right, and sulfonation is pretty similar, same sort of reactivity, but we're going to use a new reagent we haven't seen before, and this is called fuming sulfuric acid. Yeah, it's really angry. No, a lot of people actually get confused with this. I think it was in grad school, one of the students that was working in the lab thought that fuming sulfuric acid just meant hot sulfuric acid. And I was like, no, that's not what it is at all. We'll talk about that in a second. But when we treat benzene with fuming sulfuric acid, we can change this to a sulfonic acid derivative. So we don't really use these a lot for synthesis, but we will use these for other purposes later on. So I did want to introduce this, but let's go back and talk about what the heck fuming sulfuric acid is. So this is a sulfonic acid. Specifically, this is benzene sulfonic acid. There are other ones like tolulyl sulfonic acid and things like that. Yep.
Oh, right.
Okay. All right, so fuming sulfuric acid has sulfur trioxide added. All right, so let's take a look at what sulfur trioxide looks like. Sulfur trioxide can be written in a variety of different ways. Most often it's written like this. If you remember back to Gen Chem, sulfur was one of the elements that doesn't really stick firm to the octet rule. In fact, we can see that up above. Up here, sulfur has way more than an octet of electrons. Same thing with down below. The weird thing though is that oxygen-sulfur bond isn't a true double bond. In fact, there's resonance that can be drawn where you just pluck one electron over to that oxygen. Oxygen's a lot more electronegative. And you can draw it this way. Whoops, that should be an oxygen. And you can keep on doing this where you delocalize that negative charge across all of the oxygens, right? So just like with carbonate or something like that. What we do look at, though, is the nature of the sulfur. Is that sulfur going to be a good nucleophile or good electrophile? It's going to be a good electrophile, right? Because it's electron deficient. And that's what really amps up this sulfuric acid, is having the sulfur with a very strong partial positive charge on it. All right, so let's take a look at the mechanism. And just like before, we know that the electrophile has to be really strong in order for this reaction to work. And we said that that's the case because benzene or any aromatic molecule is a really crummy nucleophile, right? So if we've got sulfur trioxide floating around, that's actually going to be our main reagent. What do you think the sulfuric acid is really doing in this? It's really just acting as a solvent, more or less, which is kind of weird to think about. We normally don't use sulfuric acid as a solvent, but it allows the sulfur trioxide to dissolve really well and facilitates the reaction as a whole. So now we've got this weak nucleophile. We've got this good electrophile. And because the electrophile is so good, we can actually get this reaction to go, where one of these pi bonds will attack the sulfur and kick up electrons to the oxygen. So now this top carbon will have a positive charge. And then we'll have this new group added on. What do we call this complex again? It's, in this case, not quite a Lewis base adduct. Because we broke in aromaticity, we'd probably just call this a sigma complex or rhenium ion. I suppose you could call it a Lewis acid base adduct, though. It's just because we broke in aromaticity, it's kind of an unusual Lewis acid base adduct. All right. And then in the next step, we've got a few different options. It kind of depends which textbook you look at. In general, we typically show acid-base chemistry being the fastest, so I'm going to stick with that. And because acid-base chemistry is so fast, we could show this where we protonate that end where we've got the oxygen with the negative charge. It's kind of debatable, though. You could restore aromaticity first and do the acid-base reaction second. I'm fine with you showing it either way. And then we've got our conjugate base floating around, which is the conjugate base of sulfuric acid. All right, what do you think the next step is going to be? Yeah, the oxygen is going to grab this proton. It really, really wants to restore aromaticity. So this will collapse down. And we can end up with our final benzene sulfonic acid. So it is kind of weird, right? So the sulfuric acid in this case, we can see it acting as an acid, but primarily as a solvent to allow facilitization of the reaction to occur. Really, it's the sulfur trioxide acting as the main electrophile for this reaction. Does that make sense? All right. The cool thing with this, I'll show you this trick. Is we can install this pretty easily using fuming sulfuric acid, so we can do this forward reaction. And I'm just going to abbreviate that SO3H. That's the abbreviation for that functional group. The cool trick is we can actually pop that right back off and go the opposite direction. In order to accomplish that, what you need is dilute sulfuric acid. So what does that mean? Dilute just means it's flooded with a bunch of water, right? So you can actually remove this. The question is, well, why in the heck would you want to remove it? LabTech made a mistake. That could be one reason. Think about another situation where we added a group in just to remove it later. A protecting group or a blocking group, right? Sometimes we leave these on, sometimes we remove them. It really depends on the context of the problem, but it's kind of a neat trick that we can put this on and really easily remove it. It's one of the most labile groups we have at our disposal. Does that make sense? All right, I think we'll stop there. I'll give you a few minutes to start working on your pod if you would like, but please remember on your pod to show the entire mechanism. Don't just show intermediates for today's pod.